computer working. Good start. So, all right, as Tim said, my name's Stephen McGill, and I am an optical spectroscopist. So there are many different types of spectroscopy. I do optical spectroscopy, so I particularly specialize in the region of the electromagnetic spectrum that involves the colors of the light that you see. And we'll talk more about that. But it turns out to be a rather narrow band of the entire electromagnetic spectrum. So we'll talk about how we actually work with that particular range of frequencies and wavelengths, what we use them for. And I especially want to focus this morning on the tools that you use. So let me just ask you a quick question. How many of you here do optical spectroscopy? You are spectroscopists, okay? 2, 3, all right. So for you, this may be an opportunity to perhaps learn something about the tools that you use that you might not have known, or it'll give you more information about things that you already are quite familiar with. But for the rest of you that don't do optical spectroscopy or haven't yet done optical spectroscopy, this will sort of form a set of ABCs about a typical optical experiment that you would do, so that if you ever encounter this type of data, you perhaps are better informed to ask the right questions about the particular data. Or if you end up ever needing to do an experiment, you can fall back to look at sort of the basics of how that equipment works in terms of the light sources, the detectors, and the types of probes that we use in order to study samples in the visible light spectrum. So that's why I'm calling this working in visible optics at the NHMFL, because we're going to be talking about the tools that you use to perform these experiments. And as Tim also mentioned, my particular area of specialization within visible optics is doing time-resolved spectroscopic experiments. So in this particular case, some of the lasers that I use produce pulses of light rather than being CW or continuous wave, which means when you get pulses of light, and these pulses are very short in duration, you can do dynamical experiments. So we'll excite a sample with an energetic pulse, and then we'll study some aspect of how that sample changes. And in particular, here at the Magnet Lab, I do that in high magnetic fields. So we may change the phase of a material and study how its absorption, transmission, reflection changes, both as a function of that new phase, as a function of the particular energy that we're probing within the sample, and as a function of time following the excitation. So let's move into some of this. As I said, I'm working in typically the visible part of the spectrum, but it bleeds over, okay, into the two other sides. So you go into the near infrared, you also go into the near ultraviolet. Just so you have sort of a calibration for where that range lies, it's about an electron volt in energy, and higher energies and a little bit lower energies, but about within this band. And that corresponds to wavelengths that are about 1 micron. And as I'm sure you're familiar, most of visible light is in the hundreds of nanometer range. And of course, this is the basic frequency range. So what kind of energies does this correspond to, at least thermally? A good conversion to sort of keep in mind is that an electron volt is roughly equivalent to 10,000 Kelvin, all right? So we're not talking about emission of light that you would study, all right, from things at room temperature, all right? This is the energy range of the outer shell electrons. That's why visible spectroscopy is so important to chemistry, because so much of organic systems involve the behavior and the function of electrons in the outer shells. And this is the energy range of those interactions. And in many cases, for solid materials, it's also the physics near the Fermi level for different types of materials that we often use, like semiconductors, which are tuned either through engineering or through creating some other type of new material to to have interactions within that particular range. Okay, so some of the facilities that I work in, we have a superconducting magnet facility. This is the superconducting magnet. It's a 17.5 Tesla superconducting magnet. There's an optical table underneath. This is the top of the magnet here, and we have several top-loading probes that go in there. And just sort of a cartoon of the way we do some of our experiments is shown here. So we have a laser or an optical source that's set up on the table. And in many cases, we're illuminating the sample through the bottom. So there's a cold bore in this magnet, and the sample is often facing downward. And we have an optical port at the bottom of the magnet, and we can shine the light up through there. Now, you can introduce the light to your sample through a number of different ways, one of which is just through free space excitation, and a second way is using fiber optics. Fiber optics are great because it's easy to maneuver the light through the fiber down to where your sample is. It's basically a light pipe that can carry the light. But fiber optics have inherent limitations, as basically all instrumentation does. So for instance, as a person who does time-resolved spectroscopies, when you work with really short pulses of light, fiber optics have dispersion, and the dispersion stretches these pulses. So if you try to do a lot of work doing dynamics, you'll find the limitation with optical fibers is that you no longer have high time resolution. And so in many cases, I strive or endeavor to be able to do experiments in free space type of excitation. So before I tell you about the magnet that allows us to do that, which is the split helix magnet, I want to tell you about some of the other places that we work. We have a cart for spectroscopy, doing absorption, reflection, transmission, photoluminescence spectroscopy, which we can take to other cells. In this case, we're over in cell 8, and we have probes that go in and work in those magnets. But lately, a lot of the work that I've been focusing on is done in the 25 Tesla split helix magnet. Now, here's a cross-section through that magnet. The thing that's unique about this is that we have these side ports, which you see here. So these side ports, there's 4 of them all the way around the midplane of the magnet. The sample sits here in this 32 millimeter diameter bore. That's 25 Tesla. And we have these very, very large light cones that allow us to be able to shoot the beam directly in at the sample. This is a huge revolution for being able to do time-resolved optics, just optics in general, because now you can actually look in and see your sample. You can't look through a fiber, and see it with your eye unless you use some other kind of equipment. And in other cases, if you have a cryostat here, for example, that's taking up this port, and you can't use fiber optics for your experiment, the only other way to get to your sample is up through the bottom. And oftentimes that's very close to the floor. And this is the way we would have to do some of those experiments back before this magnet came online. But now we can just send them straight in. So these ports in the horizontal direction, they have an opening of 45 degrees. So by the time you get out to the edge of the magnet housing, it's a very large opening. And it's almost 12 degrees vertically. So that gives us what's called a really small F number. So we have a large light gathering capability with this magnet. So this is just tremendous. And we can talk more about that during with the practicals when we're doing some of the experiments that Dimitri described to you just previously. All right, so any optical experiment has several components, all right? One is you've got to have a source for photons. What is your light source? How do you pick the right light source? What types of light sources are there? Of course, you have to have a sample to study. And now this is what you will know, all right? If you're coming to the magnet lab, you know your sample, and a lot of times if you're communicating with me to do an experiment, we'll describe what is the correct light source, what are the correct detectors, what type of measurement do you want to do on your sample. So that's the information that you bring with you to the magnet lab. And I can help you figure out how to do that experiment. So as you can see, there's a number of different sources that we have. We have some that work in the ultraviolet. We have some that work from the ultraviolet to the visible, and then ones that even extend into the infrared. You'll notice that you can't just have one source that basically produces all of the colors of the visible spectrum. Now, you can if you use a light bulb, all right? But a lot of times, we need really high intensity light. We need coherent light. And a light bulb is not going to give that to you, all right? So you need a laser. Some of these are gas lasers, like the helium-cadmium and the argon laser. And so in those particular cases, the lines that they produce, the emissions, are very narrow, atomic-like spectra. Then you can go to dye lasers. They're liquids. And then you can go also to solids. So in a Thai sapphire, this is a sapphire crystal, much like the one Dimitri showed you, that's doped with titanium. And now you finally get into a type of instrument where you have a much larger or broader range of photoluminescence, a broader range of lasing. And essentially, the development of these solid-state type of lasers is what's made time-resolved spectroscopy possible, because you need large bandwidths in your lasing region to be able to get really good mode-locked operation, which is what produces the pulses. So to that end, we also have an amplified Thai sapphire system. This produces 2.5 millijoules. We have a second one now also that produces 5 millijoule pulses. That's the energy in one pulse. 130 femtoseconds for the first system. The duration of the pulses from the second system are 25 femtoseconds. And they're both 1 kilohertz, so a pulse every millisecond. And that's at 800 nanometers, which is sort of the best lasing region of the Thai sapphire crystal. And it turns out that you can get ultra-fast light at other regions of the spectrum, but in many cases, this involves using nonlinear methods. So you have to have a really stable environment for good operation of those types of characteristics. All right, so I said you need a light source. You've got your sample that you would bring, and you need an analyzer and a detector. So here at the MagLab, we have a number of research tools that function as analyzers and detectors. The first is a 3/4 meter McPherson spectrometer. We have several different spectrometers. Dimitri has a Trivista, which is for doing Raman spectroscopy, and other just high-resolution spectroscopy. We have a number of CCDs that are tuned to work for detection in either visible range to the near-infrared or further into the near-infrared. So that would be our CCD, silicon-based CCD, and also a liquid nitrogen-cooled in-gas array. And we'll talk a little bit later about why you put liquid nitrogen into these. We have many different types of fast and large area photodiodes. We also have balanced photodiode detectors. That's for common mode noise rejection, which we'll also talk about a little bit later. I operate a streak camera. This is for measuring very short pulses of photoluminescence. And that has 2 picosecond resolution. And then a bunch of photomultiplier tubes for really low-level light detection. You can actually use these for single photon counting if you need to do that. We have a number of probes, and the list of probes keeps growing, especially now that we're building things in the split helix magnet. These are just a few snapshots of some of the probes that we use in other resistive magnets. We have ones for doing Faraday reflection and transmission. So when I say Faraday reflection or Voigt reflection and transmission, I'm talking about the magneto-optical geometry, right? So in the terms of Faraday, we're talking about the K vector of the light and how it's aligned. It comes in along the field direction, and that gives you access to different magneto-optical properties that Voigt doesn't give you access to. So for instance, we can measure the magneto-optical Kerr effect. A lot of times if you're trying to measure the magnetic properties of a thin film, you might want to do Kerr effect spectroscopy. In that particular case, you send in linearly polarized light. It reflects off the sample. As the magnetic moment of the sample changes, you see a rotation in the polarization angle of the light. And by measuring that rotation angle, you can essentially map out a hysteresis curve of the sample's magnetism. We also have, to be used with the street camera, fast optics probe. In this particular case, for transmission, there's graded index fiber that comes out. So a graded index fiber has an index of refraction across the face of the index that varies as you move away from the center. One of the things this can do is reduce the dispersive properties so it doesn't stretch your pulse as much. So for instance, we can get about 10 picosecond resolution coming out the end of that fiber. So that preserves a lot of the time characteristics for photoluminescence that we really strive to keep. What types of information can we get from doing optical spectroscopy? Well, remember I said in this wavelength region, you're tuned to the, essentially, chemistry, right? The physics of what's going on in the outer shell electrons in many materials, especially in terms of life functions. But also, photons are discrete chunks of energy. You can think of them this way as quanta. So you're looking at electronic structure. Remember I said at electron volt energies, you're not working at thermal energies, right? This would be equivalent to 10,000 Kelvin. So this is electronic structure that we're looking at. So electrons make these transitions either by absorbing or emitting a photon, and so we can detect the electronic organization of materials. For solids, that can mean the crystal field splitting, spin-orbit transitions, band gaps, the Zeeman effect, if you apply a magnetic field. Photons have momentum also, and they can scatter elastically or inelastically. Again, this is Raman spectroscopy, infrared spectroscopy. Wave nature of light. You can also think of light as an electromagnetic wave, and we define a polarization. Polarization describes the time-varying electric field of your light wave. The polarization can be affected by the dielectric properties and magnetic moments of a material, so you can study magnetization as well as crystal structure. And then if you get to really, really high intensities, which are available in ultra-short pulses, you can probe nonlinear light-matter interactions. One of the tools that exemplifies this is something called second harmonic generation, and you can probe antiferromagnetic symmetry with something like that. That's just a small snapshot of the things that you can do. So now I want to move a little bit deeper into talking about some of the tools that we use for analyzing and detection. So just about every experiment that you do studying absorption, reflection, transmission here at the Magnet Lab is going to involve a spectrometer. And so I'm just talking about a visible light spectrometer. You've probably used one in your labs learning physics, all right? And you may have one in your lab now, whether you've used it or not. But this uses a grating. I'm not talking about Fourier transform type of spectrometer. But I want to talk to you for these visible light spectrometers. What are the basic tools that you need to understand so that you can use one properly? And so having worked with a number of people that have come in that have been novices in doing this type of spectroscopy, I've tried to compile a list of sort of the common misconceptions or mistakes that people make, and that's one of the things I want to address while I'm talking to you this morning. So, important points to consider when using a spectrograph. One is the dispersion, all right? So, this is the change of the diffraction angle per unit change of the wavelength. And typically people want a high dispersion. Why? Because you're using the grating in the spectrograph to space out the different wavelengths of light so that you can analyze it. You want a large difference spatially between one wavelength and the next adjacent wavelength. And that gives you the ability to resolve changes in the spectrum. So a high dispersion can be achieved by a grating with a large groove density. So if you remember, diffraction gratings, specifically a reflection grating, is often ruled, so it has a lot of lines on it. One other common example that you might see in everyday life is like if you flip over a CD or a DVD, you can see this type of diffractive effect on the underside of it. Another point to consider is the resolving power. Okay, this is related to the dispersion, but it is the ability of the spectrometer to separate two adjacent spectral lines. Dispersion is what gives you resolving power, and so they're related in that way. The resolving power is essentially this integer m, which we call the diffraction order. And n, capital N here, is the number of illuminated grooves. So this is very important. First of all, you want a grating with a high density of lines, all right, to give you large dispersion. That talks about the separation of wavelengths. But you can have a huge grating with lots of lines on it, but if you don't fill the grating with light, it's the number of illuminated lines that gives you the resolving power. All right, it gives you basically thin peaks, diffraction peaks that are coming from there. All right, so you have to have a grating with a large groove density, and also you need to fill it with light. The analogy there is to multiple slit diffraction, right? The difference between single or double slit diffraction and many, many slit diffraction. And as you remember, when you have many slits that are diffracting, you get very, very sharp maxima, and then the minima are very dark in between. Okay, finally, the other point that you should consider is the bandpass. So how much spectral bandwidth is being seen for a given wavelength position? And this is related to something called the reciprocal linear dispersion times the output image width. So another aspect of these spectrographs not only involves the grating that you use in it, but also the input and the output slit. Now, in many cases, we take away the output slit and we put a camera there. So a linear array of photodiodes, which is often just a CCD. And we leave the slit on the input. Now, if you open the slit very wide, it ruins your resolving power, okay? But it can also affect your bandpass. So the idea is, in one snapshot of your camera, how much of the spectrum do you want to be able to see? Okay? This is what the bandpass is considering. So do you want to see a small area of the spectrum, or are you doing a survey and you want to see a much larger region? Are you looking at 200 nanometers of range, or are you just trying to look at what's happening over 10 nanometers? All right. So just to summarize, a higher groove density grating improves the spectrometer resolution because it increases the dispersion or the angular separation of the wavelengths. However, it is also important to make full use of the size of the grating because the width of the diffracted maxima are narrowed according to the number of the illuminated lines, capital N. All right, so here's the famous diffraction equation. And if we use a small angle approximation, that angle is approximately the wavelength divided by d, which is the separation of the slits in the case of slit diffraction or the rulings in a diffraction grating. Now, some other important results. This is building up to an example here now. What about the separation of the maxima at different wavelengths for the same diffraction order? Typically, we're working at first order diffraction. All right, so m is going to equal 1 in all of these cases. Well, so a small change in the angle is given by the formula m delta lambda over d. In order to resolve this small change in wavelength, this angular separation must be larger than the angular width of the maximum at lambda. Okay, again, the angular width is determined by the number of illuminated gratings. So we have that width proportional to lambda over capital N and the line spacing. So therefore, the condition for resolving the lines between lambda and lambda plus delta lambda is m delta lambda over d must be greater than lambda over nd. And therefore, we get the condition resolving power mn, in this case we're thinking of the first order, m equals 1, must be greater than lambda over delta lambda, the wavelength that you're working at. So therefore, resolving power of a grating increases with the diffraction order and the number of illuminated lines. Spectrometers with long focal lengths and narrow slits also assist in obtaining the highest performance from a grating. Okay? Now, the other aspect of this is on the output slit. You don't have an output slit in the case of a CCD. So what also determines it on that side, since the output slit is important? Well, in a CCD, it's the size of an individual pixel, all right? So an individual pixel is what gives you your resolution in the detection. So you're looking for the smallest size pixel that you can get. And often I tell folks that you use in the calculation for the bandpass whichever is larger, the input slit or the size of the pixel. So for instance, if you have the input slit closed to less than 20 microns is typically the size of a pixel in the camera. So in that particular case, you don't want to use a value any less than 20 microns in your calculation of the actual resolving power, okay, or resolution. All right, so a quick example. We can talk more about this at the practical then when we're doing some of these things hands-on. But as an example, say you have a 1200 groove per millimeter grating, and it's 110 millimeters on the side. This is the kind of gratings that you have in the McPherson, for example. We're working at 500 nanometers in first-order diffraction. What is the resolving power? This is just a unitless number. It's 1200 grooves per millimeter times the size of the grating. So you get this number, 132,000. That gives you a theoretical bandpass, okay, resolution limit. So this is with the slit closed, all right, of 500 nanometers divided by R. So you could potentially get 0.0038 nanometers. But don't expect that, all right? In practice, the problem is when you reduce that slit, you reduce the amount of light that's coming in. So unless you're using a photomultiplier and spending a lot of time integrating your signal, you're not going to get typically this. All right, now let's introduce some spectral bandpass to it by opening the slit to 100 microns. And you can see now that your resolution becomes about, well, a tenth of a nanometer, let's say. That's still very good because it's about a half of a millielectron volt of resolution. Of course, that's at 500 nanometers, near the middle of the visible range. And the other aspect is linear dispersion. We'll talk about what this cosine of beta is. It's an angle between the grating normal and the diffracted wavelength. But this tells you essentially how much resolution or bandpass you're going to get as a function of the opening of the slit. So, to summarize, to achieve maximum spectral resolution, use a large grating, fully illuminated with dense rulings, use a spectrometer with a long focal distance, and reduce the entrance slit width as much as it is practical. Many of you have probably heard about holographic gratings. Typically for ruled gratings, there's something called the blaze wavelength, and that's where you get the highest reflectivity. And you typically use a holographic grating where the groove density is 1200 grooves per millimeter and higher because it's hard to make rulings at higher densities. So you can do that holographically. All right, so moving on from the spectrograph, let's talk about the detector. What are some questions that you have to ask yourself when picking a detector? Well, what is the spectral operation range? What's the relationship between the incident photon energy and the electrical response of the detector? What is its responsivity? That's the ratio of the electrical signal's output to the input power. And this is going to be highly dependent on your working wavelength. And then what is the time constant? So are you trying to measure something happening in your sample that's fast? Or don't you care? Is it slow? Are you going to be integrating for a long time? What's the time constant? Typically, the photodiode internal capacitance increases with surface area. So smaller surface area photodiodes are typically faster. Larger area ones are easier to work with, but they're slower. And then ultimately leading to what is the noise equivalent power. This is the incident power of light required to produce a signal equal to the noise in the detector. All right, so one of the first things to ask yourself if you're not seeing any signal is, am I getting enough light to be able to distinguish anything from the noise that I expect to see in the detector? So let's talk about noise, a very important topic. What are the different types of noise that are important for photodetectors? Well, there's a type of noise called dark current. This is due to the thermal emission of electrons by the photocathode. It varies with time, and it can be reduced by minimizing the area of the detector and cooling the sensor. Shot noise, that's noise associated with the discrete nature of the current, electrons. Okay? If the current produced by illuminating the detector is smaller than the shot noise associated with the dark current, then the signal is not detectable with the sensor. And then finally, Johnson noise, which is due to the thermal motion of electrons through the various internal resistances of the sensor. Typically, this is less important than minimizing dark current and the shot noise. So let's do an example. Suppose a photodiode has a dark current of 2 nanoamps, a shunt resistance of 500 megaohms. Its responsivity is half an amp per watt, and we're just going to assume a 1 hertz bandwidth. So the shot noise, all right, is according to this formula, we're getting something that's around 25 femtoamps. The Johnson noise, you can see, is related to the inverse of the resistance, whereas the shot noise is directly related to the dark current. So in the Johnson noise case, it's about 5 femtoamps. You can see the shot noise here is the dominating noise. We can add those together in quadrature to get around about 26 femtoamps total noise current, most of which is coming from the shot noise or the dark current of the detector. So therefore, our noise equivalent power is going to be about 51 femtowatts. That's what you've got to be getting on there. So, I mean, it's usually not very hard to get above that range. But if you're working with a sample that is not very generous with photons, that can be very important. And especially in the magnet systems, a lot of times you have long working distances, right? So if your light is spreading out, the edge of that wave, by the time it gets out to a collection optic or your detector, the flux of photons through a small opening, the slit in a spectrograph, might not be many photons. And of course, when you're sitting at 25 Tesla or 45 Tesla, time is key, right? You want to be able to do the measurement quickly. Let's talk now about some ways to optimize the signal-to-noise ratio, given that we've just had a short discussion about some of the noise sources and challenges of working in a high magnetic field. So one of the ways, of course, is by averaging. So a collection of photons by the photodetector is a Poisson process, for those of you that are familiar with some statistics. Therefore, the signal-to-noise goes as the square root of n, where in this case n is the sample size. 100 samples improves the signal-to-noise by a factor of 10, but it requires longer measurement times. One other way, okay, to improve this is to use something called a lock-in, which typically operates in the range of a few hertz to 100 kilohertz. There's ones that work at higher frequencies too. So just to give you an example of how you would use this for an optical experiment, in working with lock-ins, you know that a lock-in is going to take a reference signal and it's going to work to reject noise at frequencies that are not at that particular lock-in frequency. So we can do an optical experiment using this by introducing some sort of periodic modulation into the light. So you use something called a chopper to do this. It's just essentially a windmill that you put, and it basically turns the optical beam on and off at a particular frequency. So now the signal in your sample, if it's being produced by the optical excitation, it should also have that periodicity to it. And so you can use that in order to reject some of the noise coming in your input cable by introducing a periodic variation in your excitation. So what are some common sources of noise? Well, obviously, you want to avoid the lower frequency end because there's a lot of things going on there. Also power lines. So typically with choppers, you're working somewhere in the hundreds to a few kilohertz. And there are also different types of ways of chopping the beam. You can use things like photoelastic modulators, which you can get, and you're modulating there the polarization of the beam. You can also use acoustic optical modulators, and you can chop essentially in the megahertz range. Another way of optimizing the signal-to-noise ratio that we often use here is using a boxcar integrator. So there are some cases in which a lock-in may not be appropriate for what you're doing. many cases with our short pulses of light, they are coming at a particular frequency, but the signal or the response in the photodetector is very short, right? So when you're using a lock-in, you're looking for something that's periodic, so the pulse laser meets that requirement, but the duration of the pulse in your detector is maybe 100th of the total time, all right, of the period. So for instance, if it's 1 millisecond, you're operating at 1 kilohertz, you're averaging a lot of zero signal in. So the amplitude in the lock-in can be quite small. One way around that is to use a Boxcar integrator, and essentially what that does is it's going to open a gate over which it integrates, and you can center that on your pulse, and it will reject essentially everything else. So you're eliminating the noise that's coming in while there's no light shining on the detector, but it also focuses on integrating only while you have signal, which is set by the gate that you choose, and so therefore you'll get a much higher response than you might get with a lock-in. And I'm just kind of skipping ahead here because we don't have a lot of time, but I also wanted to tell you a little bit about our streak camera. So we talked about the lock-ins, we talked briefly about a Boxcar integrator. You can use a digital oscilloscope if you're measuring signal from a photodiode. Those have the flexibility to measure in the nanosecond to millisecond regime. But what if you're trying to measure like a photoluminescence lifetime that is extremely short? And we've done that here. So a group came and was studying superfluorescence emission from gallium arsenide quantum wells, and it turns out that the duration of that particular superfluorescence can be 100 picoseconds or less. So we used a streak camera to be able to measure how the duration of that superfluorescence changed as a function of magnetic field and temperature. And so the way that particularly works is that you send in a pulse of light and it hits a photocathode, and at that point it converts the light pulse to a pulse of electrons. That pulse of electrons goes down a streak tube, and essentially there's an accelerating voltage between that photocathode and the screen at the end. And then there's also a fast generator that sweeps a voltage across essentially what's represented here as a parallel plate capacitor. And so what happens is as you sweep that voltage, it spreads out this packet of electrons, which then impinges on the screen here, and then vertically you get an analysis of the time of the duration of that pulse. And that's called a streak tube, and that's how it operates. And of course, so there's a lot of very complicated electronics that are going on in order to be able to sweep that voltage very quickly, and then to be able to convert that stripe that you get as a result of that into a time, but that's what the streak camera is doing. All right, so working with optical detectors. Now here's something that is very easy to forget, and I want to stress it because it's important to remember this. And if you forget this, a lot of times you won't see any signal, and you have to correct it before you move on. So you have to remember that the output of photodiodes and photomultiplier tubes is current. It's the photoelectric effect, all right? Photon comes in, electron goes out. These detectors output a current that is proportional to the intensity of the incident light. However, most detectors, amplifiers, measure variations in voltage, right? So if you just plug in your cable from the photodiode or the photomultiplier into the lock-in, the lock-in's going to say, you know, not really what I was looking for, okay? And you'll be displeased with what you see on the detector too. There's the signal. So the problem is the input impedance for a lot of really high performance detectors, amplifiers, is very high, okay? And therefore, what you're doing is you're dumping your small current that's produced in your photodetector through a huge resistance. This creates an RC circuit, and if you're measuring something at a high frequency, you basically have rolled off, filtered away the signal that you're trying to measure. This is why a lot of times people use a 50-ohm terminator. So if you've ever seen this being used with a photomultiplier or a photodiode, they put a 50-ohm terminator at the point where they're attaching the BNC to the input of the lock-in Boxcar integrator. Why? Because as you reduce the resistance, you're essentially raising the passband of that RC circuit, right? So you can get your high frequency information. You haven't rolled it off or filtered it away. So you don't want to inadvertently filter away the signal. Alternatively, you can use something called a current preamp, all right, or a transimpedance amplifier, which are meant to receive that current and convert it to a voltage with an amplification factor involved. So, for example, taking a transimpedance amplifier as part of the detector circuit will also introduce additional noise, raising the noise equivalent power. And so remember that the noise equivalent power is the ratio of the noise current to the detector responsivity at a particular wavelength. So in this particular case here, a very simplistic diagram of a typical amplifier circuit. You have your feedback resistor, all right, and typically you have a feedback capacitor. This sets the RC filtering of the circuit. And CF, the feedback capacitor, must be reduced when increasing the feedback resistor in order to maintain the bandwidth. And so the point is that the Johnson noise of the feedback resistor is involved, but remember we can reduce that by making that feedback resistor larger. That also tends to increase the gain. And we also have to take into account the amplifier noise current flowing through the feedback resistor. So an op-amp is a very simple example of a differential amplifier, this being the op-amp here. But we can use this same idea in optics, differential amplification, to achieve a high rejection ratio of common mode noise. That is, eliminating noise that is common to both input channels of the amplifier. So therefore, you can have a reference from your laser going into one channel and the signal after it goes through your sample going into the second one. And in subtracting them, you can subtract away the noise fluctuations of the laser. And I see that we're out of time, so I'll just show you my last slide here, which is I have a wiki, all right, that's online. I can give you the address later at the practical, but it helps to summarize some of the information I've talked to you about today, and I think it'd be very helpful when you're preparing your experiments to come to the Magnet Lab. So thank you very much for your attention. Yeah, sure.